Hello and welcome back. In the next series of videos we want to take a closer look how we work with SQL. It's a very brief and incomplete overview, but at least you get the general idea. So we start with part 1, how we query a database. SQL stands for Structured Query Language. It's a standardized programming language to interact with relational databases, and it goes back to the 1970s, and the first standard SQL was in 1986. The current standard is SQL 2023, so you can see that it's an old language, but it's well developed over time. SQL actually consists of several sub-languages. There's the data query language, the data definition language, the data control language, and the data manipulation language. Essentially all parts that you need to create, fill, update, delete, organize tables and databases, and move all the data into the database and out. So SQL, the standard is very complex, and not all systems or vendors follow the standard completely. So even if we strive to follow the standard, we will need to modify the code that we develop when moving to a different system. Here in this example, we'll use PostgreSQL and keep as much standard as we possibly can, but if you use other databases, you may have to modify the code that we discuss here slightly. First of all, we need to have some definitions what we mean. Relational databases are ACID compliant, so that means there's an all or nothing. All commands are either successful or they fail, even if the server crashes in between. That has the benefit that the database is always in a defined and consistent state. So a statement is a single command in SQL, and a transaction is a block of statements that should be treated as one. So the whole block of statements, the transaction, is either successful or it fails. This again has the benefit that if we have multiple transaction statements in a transaction, we can guarantee that the database doesn't move to an indefined state even if the server loses power in the middle of it. So how do we create a transaction? We say begin transaction, and then we have a semicolon to indicate that now this command ends, and then we have a block of statements, and then either we need to commit this tells the database now execute what I've just told you, or roll back and say don't do it. So before we start working with the database, we need to prepare a database schema. That we can actually do on pen and paper and describe which tables we have, so which entities do we need to describe. How can we split this into appropriate tables? Think again about database normalization. Which data types do we expect? Which data types should the variables have, like string or float or integer or something? And how should these tables be related? Notably, the databases can have several independent schemata, so we choose an appropriate name for the schema we want to work in. Let's start with the minimalist examples. We only have two tables with very few variables or columns. Of course, in a more realistic scenario, we have many more tables, like, for example, not only samples and storage locations we have here, but also instruments, experiments, and so on. And we have many more columns, but let's stick with the simplest possible example that we can give. So we have one table that defines our samples, and the columns define the variables with defined data types, and the rows define the different samples that we have. Consequently, also the storage, we only have here like two variables, last update, when we modified this value, and more importantly the storage location. Here the rows correspond to different storage locations, and we notice that we can build relationships by using the primary key, the storage ID in the storage table, as a foreign key in the sample table. We assume for now that the tables are already filled, and we'll have code to do that for us. We will also look at how we can do it ourselves. So the first thing that we want to do is, for example, query what's in the database. And the general structure of such a statement is select, so that tells the database, now look at the columns from the table that I'm going to specify and give me the values of those. So select the columns from our tables or relations or something, where maybe we have some constraints, for example, all the samples that were added last year, And we may put them into groups and add more constraints and so on. And then we may want to impose a different order or look at only a few of them. The ones highlighted in red, select, from, and the final semicolon is the minimum that you need to do for a query. Everything else is sort of on top of that. Note that the order of the words in the query is fixed. So we need to keep the SQL keywords in this sequence. So how does it look like for our simple example? Select star, where star actually means like give me everything, all the columns, from, and now we need to specify a table. Let's take the storage table from our RDM schema. So select star from rdm.storage schema.table, semicolon, returns the following screenshots, or the storage locations that we have in our database. You can also do the same thing for samples. And now build a bit more complex requirement. We can add constraints. So select sample ID, sample name and storage ID from the samples tables where the sample storage ID is 3. That only gives us one element where the storage ID is 3. Of course, in this simple example we would have to know what storage ID 3 corresponds to. If we have more results, we can order them, for example, alphabetically. What we just said in the previous example, where we have a selection on the storage location, we can have to know which storage location we look for. So we treat each table individually, but we designed the tables to be linked. So we want to avoid having to know this number. Here we put two tables together in our query, and that's called a join. So we add columns from multiple tables and tell the database how to match the entries. And this is what the primary on the storage location table and the foreign key is for. So how do we do this? Now we have two tables, so we can select two columns from those tables. From samples we collect the sample name, and from storage we collect the storage location. So we start with the samples and then join the other table, like combine the two. We add the storage one to the samples. Now we need to tell the database how we're going to do this. So we do this join on the storage ID. Remember, if I go back, the storage ID appears twice. Once as a primary key in the storage location table, and once as a foreign key in the sample table. So here we make use of that, and we require that the match is made on this specific value. So where the storage ID in the samples table is equal to the value in the storage ID. And if we do that, we get two columns back from both tables, sample name and storage location, and this is now the human readable part where we can locate the sample in the storage location, and we don't have to know about the internal representation in terms of IDs. There are different types of joins illustrated here. We have the inner join. This matches like the red area, the overlap. We have the left outer join, the right outer join, and the full outer join. Essentially, as you can see from this Venn diagram, which part of the union or the intersection of the two tables we look at. What we actually need depends on the use case, but mostly we want the inner join where we have like the overlap between the two tables, or in other words, the matching records in both tables. If we want to experiment with this, we have to specify left and right or outer join, and you can see here from the examples that if we use the right join, we have an additional line here on the right hand part there. There is no sample stored in the storage location, but the join returns it and says, okay, there's nothing there, so I return a null value. Typically, we're not interested in those, and this is what I mean. We typically use the left or inner join. There's one specialty that we should also mention, that's called views, because we have many of these complex queries with multiple joins, for example, and we need to repeat those frequently. We can either write a small script to do that for us, or we can also make use of the database engine and store these as a view. So the database doesn't create new tables for this, but it knows how to create this combined table. And we do this with the command create or replace view. And we can give it a name and then put the query we just did. And if we want to do that, then we can just select everything from that view. That essentially is a shortcut to telling the database, look, I want to do this query and I'll just use it so frequently, I'll give this query a specific name. So information in databases is organized in table, and we've now discussed how we can retrieve information with the select command. Now we can retrieve all columns or just specific ones, and we can also combine tables with a join command. This makes use of the relations from the schema design, so we can, for example, not have to remember the different storage IDs, but we can relate the information in different tables. As a convenience functions, we can use views to store those queries we execute very frequently.